Hey everybody. Okay, let's go over some examples of solving kinematics problems. So let's say you have an electric car and you're going this fast and you accelerate this much. And like this is going to be what is common in the future, right? Electric cars. I mean, the technology is so advanced. So for example, I used to work in underwater robotics and I've worked personally on this type of technology with traction control where I could monitor the torque per propeller and as well and the propeller speed, and using that information develop an algorithm to do effectively traction control per thruster to minimize the ventilation or slip. It's exactly analogous to if you have an electric car, you could have one motor powering the front wheels, or like one motor for the front wheels, one for the rear, or you can have four independent motors, one per wheel. And you could do this traction control per wheel. So imagine that you can drive in slippery conditions, in off-road or in the rain, and you can tune the motors so that it delivers maximum torque right below the threshold before the wheel starts to slip. So, and I've done this work personally on underwater robotics from 2003 to 2010. So this is not like the technology of the future. This is like old news, right? So, okay, so let's get back to our examples here. So solving kinematics problems, there's a strategy. And the strategy is all about figuring out what you know and what's yet unknown. So whatever you encounter, the first thing you do is you think of all the formulas in the world that I know, which ones pertain to this question? Then you're like, okay, the formulas I know that pertain to this question, let's say this is happening just in the x direction. So I know things about kinematics, like this acceleration is constant. So because it's constant, I know that this is true, and I'll label these, and this is true. Assuming constant acceleration. Okay, so now that's formulas I know. Now you look at what information is provided to me. Okay, so I know this is velocity, this is acceleration, I have time, I'm looking for displacement. So look at your formulas and figure out what you know and what you don't know. So I don't know displacement here. So displacement is actually x minus x naught, right? Delta x. So let's say I put my origin at 0. So let's say that's 0. So here's my unknown. Do I know the initial velocity? Yes. Do I know time? Yes. Acceleration? Yes. Okay, so I have this unknown. And then here, find velocity. So that's this. Do I know the initial velocity? Yes. Acceleration? Yes. Time? Yes. Okay, so look, two unknowns. And I have two equations. You can solve two equations, two unknowns, no problem, right? So that's the strategy. And then you just plug numbers in, right? So next you would simplify the algebra, which this is kind of already simple, right? But simplify it before you plug any numbers in. You want to simplify it first, because what happens is oftentimes things cancel. So if you just start plugging in numbers right at the beginning, you're basically wasting time. So it's more time efficient to simplify the algebra first. Okay, let's try another example. Same strategy. So now let's say you're driving a truck, and then this is not a full electric truck, it's like a hybrid. But the engine side of it really should be biodiesel, right? Made out of corn or algae. Okay, so let's say same strategy. What formulas do I know in all of the world that pertain to this question? And then again, this is constant acceleration, right? So then I can write formulas that I know that pertain to constant acceleration. I know these two. Okay. Now let's figure out the unknowns. And you kind of see me like I make the underline. I really do this in real life, not just like for class. And this is actually an important strategy to really circle or underline your unknowns because it makes solving the math easier. So what's unknown? Position. Here. So I actually know it. I can set the initial position to 0, or x minus x naught is 2. So I know this. Initial velocity. Yes. Time. I don't know. Well, this is part A. Right, so part A. I don't know the time. Acceleration. Yes. Oh, I know it. So time, I don't know. Okay. This is part A, right? Velocity. Yes, no. Oh, I don't know. This is final velocity, I don't know. Initial velocity, 12 meters per second. Got it. Acceleration, got it. Time, I don't know. So for part A, I got two equations, two unknowns. Right, look. T and velocity. So no problem, right? Just solve one of them for t and plug it into the other, which actually we did that last time, right? 1 and 2 combined. And then we got this other formula, x minus x naught. Right, so if we look here, actually, right, this is what we're looking for. We know this already, that's 12. What is this? 3 or negative 3? This is like you're slowing down, right? So that would be negative 3. And then displacement, 2. Right, so for part A, you could just use this for part A. Okay, and then part B, how long to stop? So then I can use, for part B, those same equations. And then you decide what's known and what's unknown, right? So I got initial velocity, I got the acceleration. So I got the initial velocity, got acceleration. I don't know the distance to stop. I don't know the time to stop. This, if you come to a complete stop, that's 0, right? And then I know this. So there we go. two equations, two unknowns. The question was, how long in time does it take to stop? So then I would just need this equation for part B, right? And then this one, who cares? That could be a follow-up, like what distance do you travel before you stop? Then we could use this, right? Okay, so try and practice the strategy. It's the strategy that's important, right? Find your equations, identify the unknowns, and then you substitute. Okay, thanks for listening. I'll see you in the next video.